Hi guys. Okay, so in this video, we are going to look at the reaction yields. So we will understand what the concept of limiting reactant is. And based on that, we will be calculating the theoretical yields and then the percentage yield. So first of all, what is a limiting reactant? Limiting reactant, as the name says, reactant applies to the reactants. So when we conduct a reaction, we set up the reaction conditions and we add a certain amount of reactants, and then we expect a certain amount of product to form. So the amount of product that we can attain, that depends on how much of the reactants was added in the reaction mixture to begin with. So if we want to increase the amount of product, we will have to make changes in the reactant side. So a real life example of this is here. So here is a situation where we want cheese sandwiches. We want to have cheese sandwiches, okay? So cheese sandwiches would mean 2 slices of bread and then the cheese in between. So in the case 1, we see that there are 6 slices of bread, right? And there's a large excess of cheese. So that large excess of cheese is of no use to us. We can only make 3 sandwiches, one slice of bread, put the slice of cheese, and then bring in the other slice of bread. So this way we can only produce 3 sandwiches, and that we are limited by the amount of bread we have. So in this case, limiting reactant is the bread. Next scenario is we have large excess of bread. Okay, so we have large excess of bread, but we have very small amount of cheese. So here you see there are 18 slices. Those 18 slices, one on top of the other, can produce 9 sandwiches. But how much cheese do we have? We have only 5 slices of cheese. So we can only make 5 cheese sandwiches. So in this case, we are limited by the amount of sandwiches we can produce, but we are limited by the cheese, by the amount of cheese that we have. So here we can only make 5 sandwiches. So this way, the concept of limiting reactant, it varies, it changes. So in the first case, if we want to produce more bread, if we want to produce more cheese sandwiches, what will we do? We will buy or bring in more slice of bread. In the second case, we need more of the cheese slices. So this way you make the decisions what you need to do, or you curb your expectations of the final product. But anyways, let's look at this problem number 4.12, and this is a learning check problem, and that is on page 200. Page 200. Okay, now sorry, that's actually on page 201. 200, and this is 201. Okay, so let's look at this problem. Okay, so here's this problem where 5 grams of hydrogen is reacting with 10 grams of oxygen, and we want to see how much of water can we actually produce in this reaction. So here, it's very important, first of all, there are a few things. Keep this in mind when we do the limiting reactant problem, and that's a mistake students make. For a limiting reactant problems, you are doing comparison, okay? You're comparing that when you use comparison. So in comparison, when we use hydrogen, a certain amount of hydrogen, how much of water can you produce? Okay, and then oxygen, and how much of the water can you produce? And you're going to take whatever amount is given to you. Okay, so it's always between the reactants and the products. Okay, so reactant 1 and reactant 2. So let's put this here, reactant 1 and reactant 2. Both of them, how much of the product can they produce? The amount that the reactant that gives you, So R is the reactant that gives less product, and product is P. That is the limiting reactant. Okay, so it's always the reactant versus the product. So limiting reactant. Okay, now let's do this. So as usual, you are going to be needing the strategy that you will use is you're going to take the grams of reactant A. So this is A. Let's look at this. This is A. This is B. And this is giving you AB. Okay, so first, so reactant A, convert that to moles of A, then the mole to mole ratio of AB, okay, over the moles of A. And you convert the moles to, sometimes people stop here also. Sometimes we are just calculating, so you can stop here. But if the question is asking how many grams of water can be produced, in theory, you know, so this is, we are going to take the grams of AB over 1 mole of AB. So as usual, you will see that A goes to A. So here you are going to use the molar mass. Okay, and here you are going to use the molar mass. And this is the molar mass of AB that gives you the grams of AB, and this is the molar mass of A. And the same thing you're going to do with the B also. The same step, same, repeated for B. So let me write this down. So the B is grams of B. Convert that to moles of B using the molar mass. And here you're going to take the moles of AB, that's the product, over the moles of B, and grams of AB over the 1 mole of AB. And as usual, this conversion involves the use of molar mass of B. Okay, molar mass of B. This is the molar mass of B. And the this part over here is the molar mass of AB as usual. Molar mass of AB. So just keep this in mind that the this piece is here in the middle is the molar ratio, is the moles of the product over the moles of one of the reactants, moles of one of the reactants. Okay. Moles of one of the reactants. Okay. So that's the very important part. So let's look at now this problem in which we are given we are given 5 grams of hydrogen. And so let's see how much of water can you produce. So first is relationship of hydrogen to water. Okay, relationship of hydrogen to water. So we are given 5.0 grams of hydrogen. Convert that to mole. 1 mole of hydrogen over the grams of hydrogen. Remember, the periodic table, the mass of hydrogen is 1.008. So it's okay to use 1 gram. Okay, from the periodic table, 1 gram is the molar mass of hydrogen. Okay, so here you have the so there are 2. So for H2O, 2 times 1 grams, so that's the hydrogens, 2 hydrogens. So that is 2 grams of hydrogen. So here 2 grams of hydrogen, 2 grams of hydrogen times, now comes the mole to mole ratio. So we see from this reaction, and it's always important to see reactions checked for their balancing. 2 moles of hydrogen are producing 2 moles of water. Okay, and here we only have 1 mole of oxygen producing 2 moles of water. So it's the 2 to 2. So 2 moles of hydrogen from the balanced equation is giving you 2 moles of hydrogen, 2 moles of water. Okay, now the next thing is the molar mass of water. So 1 mole of water is 18 grams of water. So that's the molar mass. So 2 hydrogens, 1 of oxygen. Hydrogen is giving you 1.0 grams, but there are 2, so it is 2 grams are coming from hydrogen and 16 grams are coming from 1 oxygen. So it is 16 grams from oxygen. So that is 18 grams per mole. All right, so now we see, when we set this up, we see that grams of hydrogen and grams of hydrogen cancel out, moles of hydrogen and moles of hydrogen cancel out, moles of water and the moles of water cancel out. Okay, so on the side, let me just put this here, just for the sake of here, right here is the molar mass of, and I'm going to just erase this part right here. So we have the molar mass calculations ahead. Just always do that on the side, even if you may need or you don't need, you should always have that piece of information. Sorry. Okay. Okay, so here, these are the, I'm going to write this here, molar mass calculations. Okay. Then we are, so once you do that, you put on the side and you just keep these 2 reactants, hydrogen, how much of the water is producing. So this is what we are seeing now. So here we see that when after all these cancel out, so we have 5.0 times 1 times 2 times 18 divided by 2 times 2 times 1. And you get, okay, so when you do the calculations, you see that you are getting 45 grams of water from when you use 5 grams of hydrogen. Okay, so let's write this down because that's what we mean. We mean that when 5.0 grams of hydrogen is used, then 45 grams of water is produced theoretically, in theory only, is produced theoretically. So basically, this is not even theory, it's calculated, you know, it's calculated unless we actually know the other reactant also. So it's calculated. Okay, 45 grams of water is calculated. Now let's look at the situation when you have oxygen. And then in that case, how much of water can you produce? So oxygen is, we used 10 grams of oxygen. Okay, so now let's just put same story, 10.0 grams of oxygen times, convert that first step is to moles. So 1 mole of oxygen over, now oxygen, and we can get the molar mass of oxygen here also, just so we have all of them in one place. So this is for hydrogen, H2, this is for H2O, and oxygen, O2, 6 to 2 oxygens times 16 each, it comes out to be 32 grams per mole, 32 grams per mole. Okay, so we are going to put here 32 grams of oxygen 2 times, now you bring in the mole to mole ratio. So mole to mole ratio of water. So what was that? Water is, it's where's the equation? Here. So we see that 1 mole of oxygen produces 2 moles of water. So that's what you will write here. 2 moles of water. Okay, 2 moles of water over 1 mole of oxygen, O2. Okay, times. And here you have the 1 mole of water in the denominator and 18 grams of water in the numerator. All right, so grams of oxygen and grams of oxygen cancel out, moles of oxygen and moles of oxygen cancel out, moles of water and moles of water cancel out. And what do you get here? You have the 10.0 times 1 times, let's do it in blue, times, so 10.0 times 1 times 2 times 18 over 32 times 1 times 1. Okay, so let's do the calculations here. Okay, so when we do the calculations, we get that 11.25 grams of 11.25 grams of water can only be produced when 10 grams of oxygen reacts. Okay, so here, when 10 grams of oxygen is reacting, then that means we are using, there is used, then 11.5 grams of water can be produced. So that's, so I'm not just saying it's calculated, it can be produced. That's the maximum. Okay, so that is the theoretical yield. This piece is also called in theory, the maximum amount that you can obtain is only 11.25 grams. Okay, no matter how much in theory oxygen, hydrogen is giving you 45 grams. Okay, but this 45 grams is only in calculations. But in theory, you will only produce 11.25 grams. Therefore, the limiting reactant is oxygen. Okay, you are limited by the supply of oxygen. So this is the way you determine. So just make sure that it is always the 2 reactants you're comparing, and you're trying to figure out how much of the final product are they giving. So this is reactant 1, and this is the reactant 2. And how much of the final product is obtained. Okay, so this is one piece. Now let's look at another problem of percentage yield. Now, when we talk about percentage yield, I have another video which goes in great length why we do that, but here we are just looking at the problems and how to solve them, from the book. So simple problems. So percentage yield, the formula is actual yield over the theoretical yield. Now, actual yield is the amount that you get in your hand after you have finished all the processes. So in theory, you can just do the calculations on a piece of paper, right? So the theoretical yield is mathematical yield only, but actual yield, like the name says actual, it is a practical yield, amount of product that you obtain in your hand after you have taken the weights, after you have dried the product, after you have put it inside the vial, after you have finished all the steps, so there is a productivity loss. Keep this in mind, that there is productivity loss because there are so many steps. Productivity loss due to different steps that, we have to perform when we do the experiments in the lab. So due to different steps, and these steps, there is a minor, loss of product. So how much you get is always going to be less than 100%. But, it's, if you get something above like 60, 70, 80%, so that is a decent amount. Okay, so now let's look at this problem, which is on page 202, page 202, and this is a problem from this is problem 4.13 4.13. Okay. And again, this is a learning check problem. And here we see what is the percentage of a reaction that produces 12.5 grams of the gas freon, and the freon formula is CF2Cl2 from CCl4. So carbon tetrachloride is used 32.9 grams of it. Okay, and excess HF. So anytime you say excess of something, so that's obviously is a large excess. So that means that this guy is acting as a limiting reactant. So what is the reaction? The reaction is carbon tetrachloride. Okay, carbon tetrachloride is reacting with 2 moles of hydrogen fluoride or hydrogen fluoride, and this gives you CF2Cl2 and 2 moles of HCl. Okay, so here, I mean, generally we find out the limiting reactant, but since we are given a little hint here that this particular hydrogen fluoride is in large excess. So if this is in large excess, that automatically means that this guy is the limiting reactant. You know, back to that cheese, lots of cheese. We cannot make sandwiches unless we know, you know, we are limited by supply of the bread. So same story here. Okay, so then now what do we focus on? We need to find out this thing that is given to you, this is the actual yield. What is given to you is the actual yield. This is given. Okay, this is the product. HF is in excess. So now we are going to only look at the carbon tetrachloride. So in theory, you need to determine this theoretical yield. Find the theoretical yield. The question is not going to say that find the theoretical yield. It's implied, but you need to do it on your own. So find theoretical yield. And how would you do that? Same thing, the same strategy. So I'm going to just move forward. Now, first of all, find the molar masses. So molar masses of number 1, carbon tetrachloride, CCl4. So 1 carbon and 4 chlorines. 1 carbon is 12 and chlorine is 35.5. So 35, just keep it 35, and then, you know, what you get here, you add that up, then that's going to give you the molar mass of carbon tetrachloride. Next is CF2Cl2, CF2Cl2. So 1 carbon, 2 fluorines, and 2 chlorines, and you get the weight of these. So carbon, fluorine, and chlorine. Let's get this. Okay, so now we have the molar masses of carbon tetrachloride as 152, and that of CF2Cl2 is 120 grams per mole. Okay, so next is we are going to first find the theoretical yield using the 32.9 grams of carbon tetrachloride that we have put in the reaction. So 32.9, let's do this. 32, I have to put this here. 32.9 grams of carbon tetrachloride, convert that to moles. 1 mole of carbon tetrachloride over 152 grams of carbon tetrachloride. Next is the mole to mole ratio. So we see it's 1 to 1. 1 mole of carbon tetrachloride and 1 mole of freon. So it's just 1 to 1 ratio. So 1 mole of CCl4 and 1 mole of CF2Cl2. Okay. Now next is grams. So 1 mole of CF2Cl2 over grams, and the grams is 120 grams of CF2Cl2. Okay, so grams of carbon tetrachloride, grams of carbon tetrachloride cancel, moles of carbon tetrachloride and moles of carbon tetrachloride cancel, moles of CF2Cl2 and moles of CF2Cl2 cancel. So this is the theoretical yield. So in theory, we are able to produce theoretical yield. In theory, we are able to produce 32.9 times 1 times 1 times 120, and that is divided by 152 times 1 times 1, and that gives you. Okay, so when we do the calculations, we get this results 25.97. 25.97. Now it's okay to round it up, but let's see how 12.5. And so in theory, yeah, so keep this in mind that in generally, unless there are impurities, so generally theoretical yields are always going to be, theoretical yield is always going to be larger in amount than the actual yield. Okay, is always going to be more, because as I said, there is a productivity loss. So actual yield will be less due to the loss in the steps. Okay, anyway, so now we have 25.97. Sorry, the formula is the percentage yield. Percentage yield is equal to actual yield. Always write the formulas, even if it kind of looks trivial, but you know, you still need to do that. Actual over theoretical yield. Okay, times 100%. Okay, so what do you get here? You are going to put the actual yield, which is given to you, and that is 12.5. So 12.50 grams actual over theoretical is 25.97 times 100%. So let's get this. Okay. Okay, so in calculation, this comes out to be 48.13%. Okay, so the book is giving 48.3, which is fine, you know, so 48.2, 48.3, but whatever it's still close or it's in that range. So percentage yield is equal to 48.20%. It's fine. Okay. All right. So this finishes this part from here. Next, we are going to look at the quantitative chemical analysis using the titration, and then there is a gravimetric analysis. Okay. So that's going to be in the next video, those two examples. All right. Okay. Thank you. Bye-bye.